myself Advani Jaishri, and today I am just going to present this presentation on fabrication of MEMRISTOR. So basically, we will start with uh, uh, what is MEMRISTOR. Basically, it's a passive component, unlike the capacitor, resistor, and inductor. It is one of the component. It's like this is non-volatile component. That's why it is known as the passive component. It is basically two-terminal component. The reason why we are using this component as a MEMRISTOR basically itself is based on the past voltage and allow to remember. And the MEMRISTOR itself, the word says it is the word used to remember a thing. We can consider an example like it regulates the flow of electric currents and retain its resistance even after the power is cut off. While considering an example like think about the pipe.
Continue.
So, like, think about the pipe, which is having a diameter in which the direction of the flow depends. If we expand, the direction changes, and if we contract, the direction changes. Make sure that the pipe's diameter remains in the sides. When the water flows to stop, it will return back to its position. This is because of the same as it works on the memristor. So there are multiple materials to create a memristor device. For now, we have been using the metal-based memristor, which are such as zinc oxide, titanium oxide, and multiple of the memristor has been created. But for now, we are going to create it a strontium-based oxide, which are basically hexaferrite materials. Hexaferrite materials, why? Because they are basically used to store. Even hexaferrite materials are the materials which can use to store the materials. So strontium-based hexaferrites, then barium-based hexaferrites. These both are two promising materials that are used for electrical properties and in structural properties. So the objective is like we are going to fabricate hexaferrite material using the sputtering technique. So what is a sputtering technique? It's basically a deposition technique which has been PVD technique, physical vapor deposition, then sputtering. So there are multiple number of the physical vapor deposition techniques. So one of them we have been using is sputtering technique. Well, it has consists of the two RF sputtering and DC sputtering. So the RF sputtering also has its own limitations and properties, well as DC sputtering also. There are multiple number of sputtering, but mostly we are going to use this RF sputtering and DC sputtering. The reason is because they are giving a prominent amount of the deposition flow rate and the deposition layers and the film thickness, what we are supposed to require to create a memristor. So we will go on step by step for the sputtering technique, how this technique is being used in the further slides. West, what is the character? Then we are going to analyze the memristor. It's to check its electrical and magnetic properties. How this, like, if we have created the memristor, then how it is being created and what are the uses, and the one device which have been created is actually working on its original properties or not. Then to investigate, for that we are going to evaluate XRD and its IV characteristics to check its switching behavior and the memristor capacity, storing capacity abilities. Then to enhance the memristor performance, to check its potential for the memory application, because basically memristor is for now it is going to be used in neuromorphic devices and neuromorphic computing devices. So that's why it's we can consider it as like neuromorphic. Our body have a synaptic system which work on this same as the memristor work on the synaptic devices, and it has the same structure eventually. And the operating system parameters which have been used for this deposition. So for the sputtering technique, there is RF sputtering and DC sputtering. So for that, we need to make sure that there are certain parameters such as gas flow, temperature, time, film thickness, uniformity, deposition rate, and density. Eventually, temperature also plays an important role. So in RF sputtering, there is there is one positive cycle and the negative cycle. In positive cycle, there is going to be current, and the negative cycle, the current is being suppressed. So we are going to make sure that the current is not provided into the direct flow, and a plasma is generated during the sputtering process. Whereas in DC sputtering, it is like a direct current which is being provided and which is the continuous program, which is a continuous current. Sorry. So firstly, we are what we are going to do for sputtering techniques. We are going to prepare the instrument. I am going to show the instrument in the next slide. This is a basically RS sputtering device. So in the left hand side, it's the chiller, and the gas is also being pursued. And the upper side, where the whole vents are given, it is the chamber. And there are multiple number of vents and the buttons which are being going to use step by step. In your left, the device which is being kept is the chiller. Why we are using that is like basically it is going to cool the system and the process, because while creating the plasma there are going to be multiple numbers of ions going to be created, and it's going to be heat the device a lot. So that's why maintaining the temperature we are going to use a chiller. So firstly, we are going to do initially for we need to create the turn on the mains and chiller, and then make sure that the vent is being closed, because of the vent. If the vent is being opened, the vacuum will be not created, and it almost takes around of 1 to 1.5 hours of 1.5 hours time to create a whole complete chamber of vacuum. Then we have to check the target and we have to close the chamber. Then we have to set the gas flow pressure, so that and make sure that the gas flow pressure is up to the limit and to the time as much we require to maintain the temperature and to create the time amount of how much we want to sputter on the device. Then there are a vacuum pumping storage, like there are multiple numbers of like we can say this number of here there are buttons we need to turn on one by one, and then after turning it on there is a time period which is almost 6 hours it takes to complete the whole process. One on one by we will going to start, and then the time also plays an important role after turning on the current, and we are going to at that time we are going to start the airflow pressure eventually. So when the argon gas, suppose we are going to take as argon gas, there are multiple number of gas. Make sure that the non-reactive gas we are going to use to it. So firstly, we are going to use it argon gas. Then argon gas is going to react with the chamber, which is the target material, and make sure that the target material and the substrate both are kept in the opposite direction. Depending upon the machineries, there are number of target and substrate are in the opposite direction. So firstly, when argon gas is introduced in the chamber, then we are going to make sure that we supply the current. When the current is going to be start, then we are make sure that the number of vacuum is being created in the chamber, and make sure that when the gas react with the target material, it's make sure that everything has been temperature has been maintained, and make sure that every parameters is being occupied. Then when argon gas is going to react with the target material, it is going to create the plasma. After creating the plasma, the positive ions and the negative ions of the target material is going to get deposited on the substrate material. Depending upon the time, temperature, it is going to deposit in the uniformity, and we are supposed to create the time before we are going to, and we need to check its RPM, rotation per minute. The target would be rotating in such a way that it doesn't get directly disc to the substrate. And yes, after creating this plasma, and once the deposition has been created, make sure that the whole process is being completely reversed. Like we need to turn off the vacuum valves, pumps, and gas flow eventually one by one, and make sure that the vent and the chamber is get opened, and remove the vacuum which has been created in the chamber. Because once we create the vacuum, make sure that it's being removed, and eventually clean the chamber, because there are multiple numbers of process has been done. So there might be eventually like it will be create fumes, or different materials has been spread into the chambers. So make sure that we need to clean the chamber even after one of the process is being proceed. If we want to deposit a second deposition layer, then repeat the process again, and then fully again shut down the device. This is the basic flow of the block diagram. We can say it as like how memristor has been created, where the bottom electrode, which is ITO coated PET, it is indium tin oxide, and it's coated on the polyester polyimide, and the polyimide is of glass material, where it makes a sandwich like structure. Its bottom layer and the top layer, and in between there is an active layer which is barium hexaferrite. There can be materials like such as strontium hexaferrite, multiple number of materials. We are just to make sure that top electrode and bottom electrode are being present, so that it's easy for its electrical connections. And the silver paste are like to connect its top electrode, and it's basically silver paint. We can use multiple number of like copper and silver and aluminum. There are multiple numbers, but here we are going to use silver because its electrical conductivity are much amount of better than any other. So firstly, what are the process involved in this fabrication? So fabrication process, in this first phase, we are going to create a base, and then ITU coat it in the amount of the barium hexaferrite which has to be deposited. So we can consider it in terms of time. Firstly, we can check for the time because that's the easiest way. How can we can go through individual one of the because in memristor we want to see what is the hysteresis loop is being created in memristor or not. Firstly, that's the main target of the hysteresis memristor. So we are supposed to check its firstly main properties to check its electrical properties. So different time would be having different thickness, and that thickness would obviously yes, there are multiple numbers of processes involved, and we will start with the firstly we are supposed to fabricate our device. That's not sure that while once we are creating a fabricated device, it's almost going to be correct. There are multiple numbers of steps how we are going to check it, and if this that passes all the tests, then we are able to finalize that yes, this memristor device is actually going to perform a desired task. And secondly, now we are going to check its electrical characteristics. Why we are going to check it? Basically, it's for IV characteristics, resistivity, switching properties. Like this connection, as you can see it in this figure. So there are the top electrodes and the bottom electrodes. Bottom electrode, it's ITO coated PET, and the top electrode is silver paste. And this in between there is a layer of the barium hexaferrite material. So what we are going to do is that we are supposed to going to set up probe station, which is four probe material, a four probe device, and now we are going to check its individual properties. So while keeping its voltage from 0 to 3 volt, 1 volt and 5 volt, we are going to check its properties. Firstly, main thing is for to check its resistive properties, we are going to check its hysteresis loop. We are going to get it in one of the devices which I have been already performed. I will show it in the next few slides while checking the its XRD and IV characteristics. Firstly, how we are going to, there is another setup for this to check in electrical characterization. Then multiple tests are going to perform to check its resistivity. In phase, then XRD, yes, XRD, why we are going to do XRD? And there are, in XRD also, there is a large concept, how we are going to do an XRD of the material. Eventually, a small device can be also be, its XRD could be taken, and the multiple, I mean, big devices also, in the XRD could be taken. There are auto sampler changer, and this is the machinery. Sometimes there are automatic machines, and sometimes there are machineries in which you need to check at each of the we can say it as angles. There are multiple, and this machinery is actually automatic sampler, so it's directly changes without just we have to cap the sample into the sample holder, and then it will by with the change in the time, it will change with the angles, and it will check the its composition and the crystalline structure. These are the results in which XRD material. So now by looking these two images, we can get to know that there is one is the material is 18 minutes sputtering device and the other one is the 6 minutes sputtering device. So in 18 minutes, we are able to see that both of this XRD structure is same because the material which we have deposited is in the PVD form, the sputtering. So the difference between PVD and CVD can be here checked, because PVD we are going to check just only physical layer. We are not going to change its interior characteristics and eventually their dimensions and even orientation. Whereas in chemical, we are totally going to change its properties, and then we are actually in CVD there are multiple number of we need to heat up the gases, and then we need to eventually heat the target and substrate, and then layer by layer it's being deposited. Whereas in physical deposition, this is the easiest process to deposit a device, deposit a thin film on on the substrate, and basically the XRD which we are using is both of these XRD images almost similar. There is just a bit of noise created between these thetas, which is the angles. From 2 theta to 8 theta, there are 2 theta. There are multiple numbers of angles. IV characteristics. Here the change is it, while sputtering to the 18 minutes, we are getting a large amount of noise, which is not acceptable for the bipolar characteristics, which is the MEMRISTOR device characteristics. So yes, the time I have fabricated multiple number of devices, which is having a 6 minute, 18 minutes, and 20 minutes, and number of while checking eventually the temperature, and I'm eventually checking the gas flow. Well, once I was having gas flow of less than 20 cubic per minute, sorry, cubic per minute. So at that time, I was not able to eventually complete the whole deposition parameter. So yes, that was the one parameter which was get affecting. And then for the time, I am not sure that it will be going to be at sputter at 6 minutes, and I am going to get its proper bipolar characteristics. And this for the 6 minutes sputtering characteristics, I'm able to get the bipolar switching characteristics and eventually hysteresis loop. I can show in this next slide what is bipolar switching characteristics. So at positive cycle and even negative voltage amount, when there is a positive voltage, we are going to set the device, and then again getting back to the negative voltage, we are going to get reset it. Like we can say it as when a computer is we are writing something on the computer, and it's storing something, and suddenly the power gets cut off. If there is a memristor, it will hold the device, whatever we have been put to the computer or any of the devices, it will store until the power regains it, and there is no issue and no data loss, so that we can check again back what we have been typed or written. This is the main new advantage we can use in neuromorphic computing. And yes, in nowadays, I mean, actually, for the next generation computing, neuromorphic computing, MEMRISTOR is going to be a good device to be implemented. So yes, this was done with the DC sputtering. And eventually, what was the reason we have not done the RS sputtering? I have done on both RS sputtering and DC sputtering, but yes, by fabricating on MEMRISTOR with DC sputtering was much more easier and comparatively not the damage, because in RS sputtering there is a continuously target is being stuck with the current one by one. So it's there is a chances that the target gets hit by the current, and it was not able to create a uniform image, and eventually target get damaged. So while this target get damaged, we are going to have a huge loss of the devices, and eventually the material is being lost a lot. And this is the reason why we are not going for the RF sputtering, and we are just moving to the DC sputtering. By achieving its bipolar and switching characteristics, we are able to make sure that the 6 minute sputtering device has been actually useful for the neuromorphic computing, and any of the its properties has been justified with the memristor. With the help of the XRD, we are going to confirm the crystallinity, that is M-type hexaferrite. There are multiple number of hexaferites such as M-type, S-type, H-type. They are having multiple numbers of properties eventually. This is basically an AI based memory and synaptic emulation. Why we have used the word synaptic is because it works as our brain cells and nerve cells. So as we can consider our hands way, so it's basically they are in a synaptic way, and this memristor also work in the synaptic way. Because they are able to store the capacity and then regain its when the device actually needed, it gives back its information which has been stored to the device. So what is going to be the future scope? Future scope is like CMOS integration, then doping and magnetic field. These are the basic we can say it as advantages where we can use this memristor device. Next, we will go for the sputtering. What is sputtering basically? So sputtering is a PVD technique. There are multiple numbers of PVD techniques such as thermal. Then just a second. I can start with there are multiple number of depositions. We can consider CVD, PVD. Firstly, we will go for the PVD. So it's thermal evaporation. So we are going to thermally evaporate the target material, and then a thin film is deposited to the material, which is heated in the vacuum, which causes to evaporate and deposit onto the thin film substrate. Here we are supposed to create firstly vacuum, and then we are supposed to create our target material and the substrate material. Make sure that both of its parameters are the main parameters are like deposition rate, film quality, target material, substrate material, and process parameters. Because in during sputtering or thermal evaporation, then multiple number of deposition techniques, there are multiple numbers of device parameters and device process parameters. So we can go for this startingly with the thermal evaporation, then sputtering, electron beam evaporation, ion implanting. There are multiple numbers of sputtering techniques. The reason we are going for the PVD is because of high quality and precise control, and it's the application are very smooth and easier to use. Because in CVD there are multiple number of chances that both of them get damaged, and it can eventually, break the substance, and we are not able to regain its the original device. Then chemical vapor deposition, that is CVD. There are multiple numbers of CVD techniques: LPCVD, low power CVD, plasma CVD, MOCVD, metal oxide CVD. Then ALD, multiple number of there: high vacuum CVD, thermal CVD, aerospace CVD. Then uh, mostly we are going to use MOCVD, epitaxy growth, atomic layer CVD, and plasma enhanced CVD. Because in atomic, it is going to do both the devices, substrate, and the target are going to melt in the form of the atomics, and then epitaxial layer grows one by one. When one atom will be fallen, then another atom will be grown, and this steps take by process. Then in the MOCVD, it's like metal. We are going to use only metals. We are going to heat them in the gaseous form. And then the metal organic compounds such as 3 and 5 semiconductor, which are actually the toxic. We are supposed to going to use toxic precursors such as gallium arsenide, indium phosphide, gallium nitride, and which are actually used in LEDs. And then low pressure, because while creating the low pressure CVDs, we are going to use that 0.1 to 0.1 to 1 0.1 to 1 torque, and it's basically used to give an excellent uniformity and control. So it's better for thin films and to eventually maintain the temperature. So where we are going to use it, metal silicates. Then we can go for okay. So this were the techniques where we are going to use this sputtering techniques and objective parameters. We have completed the MEMRISTOR eventually, and these are the operating parameters. Make sure that the operating parameters are as given by the sheet given by the this device itself. We are making sure that we are eventually following the units and the amount of the temperature and pressure given by the I mean there are multiple number of machineries, so that eventually each machine has their own terms and norms, and this machineries eventually give their booklet where we are going to use that. There are sometimes booklet. I can show you one of the booklet. Just a second to show that booklet. So by using that booklet, we are going to use to deposit the parameter by checking its parameter and what we are going to use it. We will make sure that we are going to use that itself. Not we are going to change much more because it can damage the machineries also. Are you able to see my screen? Hello.
Yeah, yeah, WhatsApp. You can see the WhatsApp.
Okay, thank you. So this is the booklet given by the sputtering machine itself, and they have already given this parameters and theory how is this machine is going to be used. We are supposed to use in that manner itself. There are some number of formulas how to the plasma is being generated. We are considering these formulas, and eventually we are just creating giving the pressure and the air, eventually gas flow also. This how this is being so yes, this is the base plate where we are going to you keep the target material, and then the shutter is being closed. So while when we are going to start the process, the shutter is being opened, then the current is going to hit this target materials, and the fumes has been created which create the plasma, and then plasma is going to generate into the whole vacuum chamber. You can see it in this image. This is the upper portion of the target material, and the lower portion is beneath the vacuum chamber. And the when the this is device has been closed, once we are creating the vacuum, this is the electrical connections how this it's supposed to be connected. And one is a power supply rotatory pump. There are numbers of pump, and each pump has its own we can say it takes time. We need to create the temperature, pressure, and we need to maintain it, because once we are not maintaining, we will not get the desired amount of thin film which we are supposed to require. This is the total machine the device like where we are going to keep the device and the target material and the substrate. This is the 3D view of the sputtering front view. Here itself they have given how what are the number names. So this is the booklet which is being provided by each of the machine, so that because this machine is not Indian based, so they are providing a booklet so that we can use it in the further eventually where we are required. And I can show you what actually sputtering device has been created. Yes. Yes, these are the multiple number of the color also changes with the deposition parameter rates and the number of the time. So firstly, when I have created 18 minutes sputtering device, which was orange color. Actually, we are not supposed to get orange color, and like there is the thread-like structure in the second device, if you can see. Hello. So this is also not a correct device. Then we are again going to create the third device, which is the complete flow of the memristor, where we are able to get the complete structure what we are supposed to do. There are multiple number of steps taken to get a perfect memristor device, or eventually any of the devices. If we are going to do for the one device, it's okay. But when we are going to check its characteristic properties, then we need to do multiple numbers of time, and we need to sputter multiple number of sputtering. Eventually, I can show.
Your voice is not coming properly. It is breaking. Hello.
Hello.
Yeah, your voice is sometimes it is less, sometimes it is more.
Okay, I will make sure that. Actually, I'm
Yeah,
already
yeah.
connected. Now it's proper.
Yeah, now it is fine.
I can show you the next step, which has been done after the sputtering technique. So then the device is being fabricated. There are multiple number of fabrication techniques. This is just one of the fabricating techniques. This whole fabrication process takes a lot, from creating a wafer to then depositing, cleaning. There are multiple number of steps. Eventually, I have been sharing through my LinkedIn also. I have shared one of the PPT which was for packaging, which was for the whole packaging process flow. It was not covering whole individual packaging flow, but yes, overview of the packaging, because it also consists of the multiple numbers of steps, and eventually they are having individual parameters. Eventually, I can show you few more images how plasma is being generated. You can see it is like this is a plasma chamber itself, and plasma is being generated while the current is being produced in the chamber. This is the plasma fumes created, and this is the device which has been created. After this is another device. It's just not same as a MEMRISTOR. This is another device which I have been sputtered like a few time ago. But this is what I want to show it, like how this plasma is being generated. Yes, as for now, I have just created this much amount of. Hello.
Yeah.
I just want to ask, like, are there any questions, or like, do you want to tell me or ask me? I'm open to it, because as for now, I just created this options itself, as I am also eventually working. Like, I am also getting an internship, so I am supposed to work eventually there, and I'm preparing for that itself.
Yeah. So everyone, you can ask your questions now. Anyone want to ask any questions? You can unmute and ask. You can unmute your ask.
Can you hear me, ma'am? Hello.
Yeah, sure.
Yeah, ma'am. So when you told about substrate, so are you using always like the material what you are use? Will it give a good conductivity like compared to silicon or
No, depends.
germ-
Okay, okay, sure. Yeah, yes. Can you complete the question?
like because when it comes to chip manufacturing, mostly people go with silicon and germanium, right? So when you use this barium and other material, will it give the same conductivity as expected? Though it's a memristor, still electrons conductivity and all those aspects come into, right? So just wanted to know, like, will the conductivity and the efficiency will be good or something?
Yes, conductivity and efficiency would be good, and eventually silicon and germanium are being replaced with the new other materials. Like for now, they are going to bring eventually this that lab grown diamonds also, and the China already has given its new. I mean, I'm not sure about the material, but they are also even launching the new materials. So yes, they are eventually giving the good amount of the conductivity, and its resistivity also it's maintained. There are multiple numbers of materials which we can use, and we can get the result what we were getting eventually from the silicon itself.
So it would be the same like how silicon used to work. So we can embed even like whatever designs we make, right? I mean, in the design part, we can embed on the chip, right?
Yes, we can. We are able to design eventually. for considering for the MEMRISTOR, yes, we are able to do that because there are multiple number of papers which are being tested, even tested for this MEMRISTOR, where we were using firstly titanium oxide and zinc oxide. As for now, hexaferrite materials has eventually not been out to the market, so this is already new to the market. I mean, there are being multiple number of research going on, but yes, there are multiple things which we are going to consider for the hexaferrite materials. We are still checking for the its film thickness and uniformity. Yes, well, uniformity is maintained because while we are going to check the XRD, we are going to get its proper. I mean, we are eventually getting the same and the actual amount of it.
So instead of photolithography, here plasma is being used, correct?
Yes,
In
yes,
this, okay.
yes.
Got it. Yeah,
We
thank you.
can like photolithography is actually a big process where we are going to use. I mean, the even the device is also expensive. As for consider is a small scale, then we can go for the sputtering or any deposition technique. So it's a kind of, we can say it as a easier way and even compact and even not costlier method.
Yeah, thank you, ma'am. I got clear.
Anyone else?
Anyone else, any doubt? Or we can end the session?